In the case of the LC oscillators, we have seen Colpitt's oscillator. We have seen, and we have calculated the frequency for oscillations. We have calculated, and next we'll move to multivibrators here. So today we are going to be study about multivibrator. So now I'll share my screen. So today we are going to start about multivibrators. So what is multivibrator? We'll see. Then we'll move to different types of multivibrators here. So today we are going to study about multivibrators. Multivibrators we are going to study. So if you see the multivibrator, so this multivibrator is nothing but it is also an oscillator, or we can say that two-stage amplifier. Multivibrator is nothing but this is also an oscillator only. So multivibrator is also an oscillator. So this multivibrator is also a oscillator, right? Or it can be a two-stage amplifier. It can be a two-stage amplifier. Can be two-stage amplifier with 100% feedback. It is going to be have. So in multivibrator, two transistors are coupled in such a way that the output of one amplifier provides an input for another one. So if you take, it is, as we said that it is a two-stage amplifier. So in this multivibrator, two transistors are coupled in such a way that the output of one amplifier provides an input for other amplifier. Like suppose if this is one amplifier, if you are having, so this is the first amplifier if we take. So this is the input which we can give in this one. So this is the input we have. So you can expect the output from here. So once output you are going to be get. So this output will be the input for second stage amplifier. So this output will be the input here. And this is the second amplifier we have. So finally, we can get the output here. So this is the final output which we have. Okay. So multivibrator is a two-stage amplifier with 100% feedback we have. So in this multivibrator, two transistors are coupled in such a way that the output of one amplifier provides an input for another amplifier. So that we have to remember in the case of the multivibrator. So the amplifiers use positive feedback. Already we have studied when we have studied about the feedback here. So this feedback, what is the feedback means? From the fraction of the output, we are going to be taken to the input. So here in the case of the amplifiers, so amplifiers here we use a positive feedback in amplifiers. Okay. So we'll use positive feedback in amplifiers, which is supplied in such a manner that when one transistor is on position, so if you take the transistor 1, so this transistor 1 will be in the on position. Another transistor, if you take a T2, so this will be in the off position you are going to be have. So, and this action is reversed after a time, depending upon the circuit condition. That means this T1 becomes off after a period of time, and then T2 becomes on here. So vice versa, it is going to be takes place in this case. So if you see that block diagram of multivibrator, so here we'll draw the block diagram of multivibrator, we'll draw here. So here we have a transistor 1. So this is the transistor 1 we have. So next we have the another transistor, that is the second transistor. This is a transistor 2 here we have. As I told that one of the output will be given as input for this one. So this transistor, so you have the input. So this is the input will be given to the transistor. So transistor 1 is taken as a Q1, transistor 2 is taken as a Q2. So this output will be connected to the input for this one, right? So final output you can expect here. Final output you can expect here. So we know that the feedback condition will be applied here. So here, from this output, some fraction of will be given as an input here. And so this is actually, there is no connection, this means, right? So here, in the case of this, positive feedback is implied. Positive feedback is implied here. So this is the transistor 1, transistor 2 we have. So this is the block diagram. So in this block diagram, if you see here, we use two transistors. So transistor 1, we have a transistor 1 here. So this one is a transistor 1 here, first transistor, whichever we have used. And this is the second transistor, which we have used. So in this, as we have taken one transistor is Q1, another transistor is Q2. So which are alternately becoming on and off position. So if one transistor is on, another transistor will be off. If one transistor is off, another transistor will be on. So alternatively, it is going to be takes place here. Suppose here Q2 becomes on here. So in this case, if you consider Q2, if it is becoming on position, so then after what will happen means first to this transistor, collector current IC 1 minute. So as we know that a transistor is consisting of 3 terminals, a base, collector, and emitter. So in this case, if you say second transistor is on first, through this transistor, collector current. So the generally collector current is represented with the IC. So this IC will flow for a period of uh, BC. Okay, flow for a period of BC. That is BC is nothing but a base on circuit components. So during this period, Q1 will be off. Q1 will be off here you have, right? So after that, Q2 will becomes off. So in the first one is Q1 is off. Second one is Q2 off you are going to be have. So in this case, whenever the Q2 will become off, the current ICEO will flow it for a period of to Q1 here. Okay. So during the period Q1 will remain on here. So here, if you draw the how the what you call on and off position will be there here. So here, multivibrator in the output we are going to be expect either a square wave or a rectangle wave. You can expect here. Okay. So this is the maximum current which we have, which we call it as a IC. So on this y-axis, IC current will be there. So this is the maximum current we have. So if I take this is a position A, this is a position B here, and this is C, and this is a D, this is E, and this one is a F, and go on continuous like this H, I, J, K, L, and M, and you are going to be continuous. So now, as I told that first one, Q2 become on first. Okay, Q2 becomes on first. So this transistor collector current IC will flow for a period of BC here. So this one. So in this case, this is the case when Q2 is in the on position. Q2 is in the on position, right? So it is going to be flow for a period of a time period. Generally, this is the time period. This is the current which we have on y-axis. So for a period of BC, the current will be flows here. So during this period, whenever Q2 is on, Q1 will be off here. Next after, whenever Q2 is off, so here Q2 is on, next Q2 is off here. So this part you are going to get. Q2 is off, this part you are going to get. And current IC will flow through it for a period of Q1. So during the period of Q1, remain on. After this period, Q2 will become on and Q1 will be off. So in this way, the process will be continuous, goes on, and you are going to be producing a square wave output as shown in this figure here. Okay, so which can be obtained across the transistor Q1 and Q2. Okay, so next, what are the terms which we are going to study in the case of the multivibrator? Just we'll look at the terms which we are going to get here. So first, we will study about what is a stable state. What is stable state here? So the stable state is nothing but it is one. Stable state is one in which current and voltages satisfies the Kirchhoff's laws and loop gain is less than unity. Loop gain is nothing but here we will take it as a G1. So its value is less than 1 you are going to be having. Okay, the stable state is one in which current and voltage satisfies Kirchhoff's laws and loop gain is less than what we call unity you are going to be having. And next we will study what is a transition. So what is transition? Transition, you should note here. Okay, transition. So this transition is nothing but it is a state of conduction transfer from the on transistor to the off transistor. Transition is the state of conduction transfer from the on transistor to off transistor. On transistor to off transistor. Next, we'll have like a switching time or a transition time. So switching time or transition time is nothing but the time interval between which the conduction transfer from the on transistor to the off transistor. So on transistor to the off transistor, whatever may be the time interval, it is going to be takes place. So that is one we will be calling it as what transition time or switching time we are going to be called. And similarly, we have like a settling time. So settling time. So this settling time is nothing but the resolving time for an multivibrator is the minimum time interval between the two consecutive trigger pulses and equals the total of the transition time and settling time of the circuit. So similarly, we have settling time, one more term which we are going to be get here. It is a delay time. Okay. So this delay time is nothing but the collector current in transistor does not immediately respond to the transition. Instead, it takes some time to rise to its saturation value. This is known as a delay time of the circuit we are going to be called. Similarly, we have like a what we call a rise and fall time. So we have a rise as well as the fall time. So these also you are going to become across in this world multivibrator. So the rise and fall times are due to the fact that IC current, that is a collector current, must travels the active region in order to make a transition from one state to another state. Means so from one state to this is the one state it is having to this time here. So this is what we call it as a, this is calling it as a rising time. This is calling it as a falling time we are going to be called. Okay, so these are the some uh, terms which you are going to come across in the case of the multivibrators. So now we'll see different types of multivibrators. So what type of multivibrators you have, we'll see here. So now we'll see types of multivibrator. Types of multivibrators. So generally, you have three different types of multivibrators we have, depending upon the type of the coupling network used in on and off states here. So first one we have is a stable multivibrator. We have a stable, or this one also called it as a free running multivibrator. So we call it as a free running multivibrator. We call it as a free running multivibrator, we'll call. And the second one we have is monostable multivibrator. Monostable multivibrator we have. And the third one which we have is a bistable multivibrator. So bistable multivibrator. So these are the three types of multivibrators which we have basing upon the network used on and off state here. Okay. So first, just we'll discuss about three different multivibrators. What are those? So then after in detail, we'll move to what is a stable multivibrator, what is monostable, what is bistable multivibrators. So first one, if you see a stable multivibrator, so we talk about what is a stable multivibrator here. So this one about this multivibrator. So this stable multivibrator is nothing but we will be calling it as a free running multivibrator also. Uh, multivibrator. This multivibrator will be calling it as a free running multivibrator. So which alternates automatically between the two states. That is in the on and off states. So it is going to be continuously alternates automatically between the two states and remains in each for a time dependent upon the circuit constants. So depending upon the circuit constant, it will be stays in the on and as well as the off positions. Okay. So this is just an oscillator since it requires no external pulse for its operation. It does require a source of DC power because it continuously provides the square wave output. So it is called as a stable multivibrator or free running multivibrator we are going to call. And next one we have is a monostable multivibrator. So monostable multivibrator has a one stable state. In the previous case, we have two stable states. So in the case of the monostable multivibrator, we have the one stable state and one quasi-stable state here. So in this case, we have a one stable state and another quasi-stable state. QS, quasi-stable state. So these are the two states which we have in the case of the monostable multivibrator. One is a stable state and another one is a quasi-stable state we have. And if you see here in the case of the monostable multivibrator, so the application of input pulse triggers the circuits into its quasi-stable state, in which it remains for a period of uh, time, which is determined by the circuit constants. So after this period of time, the circuit returns to its initial state. The process is repeated upon the application of each trigger pulse here. So in the previous case, we don't apply any trigger pulse, but whereas in the case of the monostable multivibrator, we have to apply the trigger here in this case. Trigger pulse we have to apply so that it will be continuously changes its state. So since the monostable multivibrator produces a single output pulse for each input trigger pulse, so it is generally called it as a monostable multivibrator. So for each input trigger pulse, it is generally produces one state. So that is the reason why we will be calling it as a monostable multivibrator we are going to be calling here. And another type of multivibrator which we have is a third one, which is a bistable multivibrator. So in the case of the bistable multivibrator, it has two stable states. In this case also we have a two stable states we have. Two stable states we have. So it requires the application of an external triggering pulse to change the operation from either one state to another state. So it is also called it as a flip-flap multivibrator because of the possible states it can assume. Okay, so these are the three different type of multivibrators which we have. So first we'll see about the a stable multivibrator here. In detail, we'll calculate the frequency of oscillation for this one also. So we'll see about a stable multivibrator. Right. So we'll draw a stable multivibrator arrangement, circuit arrangement, how it will be there, we'll draw that one. Otherwise, take this in this manner. So this is one transistor. This is one transistor. So this is the base. This is a collector. This is a emitter which we have. So this is the, take it as a B1 and second transistor. This is emitter. This is a collector. This is a base. Base to the hand. So now this output here will have a capacitor. In this case also we have a capacitor. So all these are connected to Let's see. These are the two resistors, R1, this R2. Yeah, this RC1 resistor. This is RC2 resistor. That is nothing but a collector resistor. So this is the first transistor Q1. This is the second transistor Q2. So now here we'll apply input pulse here. Like this. Yeah. This is one. Okay. So this is a circuit arrangement for a stable multivibrator. So it is also called it as a free running relaxation oscillator, and it is used generally for the generation of what we call a square wave generation. Okay, in order to produce the square waveform, we will be using this what we call a stable multivibrator. So it's a square wave generator. Right. So an stable multivibrator is basically two-stage RC coupled of amplifier with two identical transistors put back to back here. So this is one capacitor C, one we will call. This is another capacitor C2. So that is the reason why it's a basically two-stage RC coupled amplifier with two identical transistors put back to back. The output of one stage is becomes input of the second stage. Okay, so this output of the one is becoming the input of the another stage here, second stage that is, and the output of second stage becomes the input of first stage here. So this output becomes input for the first stage here. Okay, so this is what the circuit arrangement we have. Now, the circuit of a stable multivibrator having two symmetrical transistors. One is a Q1, okay, another one is a Q2 transistors. Okay, so these two are symmetrical transistors which we have. So the transistor Q1 and Q2 is forward biased. So this transistor Q1 and Q2 are forward biased by the power supply VCC here. Okay, by the power supply VCC through resistors R1 and R2. Now a stable multivibrator may be though of as two common emitter amplifier stages. So each stage provides a feedback to capacitor at the input of the other. So since the amplifying stage introduces 180 degrees of phase shift here. So the amplifying stage, this produces a 180 degrees of phase shift, right? So 180 degrees of phase shift we have got, and another 180 degrees of phase shift is produced by another capacitor. Okay, so amplifying stage introduces a 180 degrees of phase shift. Another 180 degrees of one more 180 degrees of phase shift is introduced by a capacitor here. So it is introduced by a capacitor. So total 360 degrees of phase shift, or we can say that 0 degrees of phase shift you are going to be get here. So we can say that the output is in phase with the input here. So the output is in phase with the input you have here, right? And the amplifier will produce this oscillations here, right? So the transistors here are driven into cutoff region. The cutoff region, that is a off region and saturated region on here. So these transistors are driven into cutoff, that is off, and saturation on states, almost instantaneously producing a square wave output here. Okay. So now if you see the operation of this a stable multivibrator, here we assume that both the transistors are identical here. So the transistor 1 and transistor 2 both are identical here. But in this, two things cannot be exactly same here. So actually we assume that Q1 and Q2 both are the same. Otherwise we can say that Q1 and Q2 are identical. But in practical, what will happen means they don't deliver same output here. So therefore these two cannot be exactly same. Generally, as we have taken it is a symmetrical, but this Q1 and Q2 are generally not same here. So hence there is a small difference between the transistors Q1 and Q2 uh, will have here. So one of the two states of first, right? So now if you see the operation here, so first what will happen means the Q1 transistor, it becomes on here. Understand? So first we have this, the transistor the one, Q1 becomes on. So here transistor Q1 is becoming on when the circuit is switched on. When the circuit is switched on, that is a plus VCC is on. Okay, so Q1 will becomes on when the circuit is switched on. That is where the power supply is on here. So then collector current will flow through this RC1 here. So whenever we are switching this VCC, Q1 transistor becomes on here. So in this case, the collector current will flow through this RC1. Collector current will flow through this RC1 here of the transistor. And the capacitor C1 will start charging here. Okay, whenever we switch on VCC, first Q1 will be on, RC1 here the current will flow in this one, and the capacitor will be charges here. The capacitor C1 is going to be charges here, and which maintains the transistor Q2 off here. In this case, whenever Q1 is on, and Q2 will be off. Already we have studied about that one. Q2 will be off here. We are going to be have, right? So what is that is in this case the transistor Q1 is on here when the circuit is switched to power supply VCC. So then the collector current will flows through this RC1, and this capacitor C1 is going to be starts charging, and it is going to be maintains the transistor Q2 is off here. Next, now the collector current in Q1, the collector current in the Q1 is going to be rises to saturation value, whereas current flowing through the transistor Q2 is equal to ICU. So in the time determined by the circuit components, the capacitor C1 will be fully charged and then discharges into the base of the transistor Q2. Okay, base of the transistor Q2 here. So it charges maximum and then discharges to the base of the transistor Q2 here. So now the transistor Q2 is on here in this case. So whenever transistor Q1 is on, Q1 becomes off here. So maintaining Q1 in off state for the determinant means for a particular period here. So again, when the transistor Q2 becomes on here, Q2 becomes on, the collector current flows through the RC2 here. The collector current flows through this RC2 here. So thereafter, this C2 is going to be charges here. So as C2 is going to be charged, so as the collector current rises to saturation uh, in Q2, in Q1, it is equal to ICO. So when the capacitor C2 is fully charged, it discharges into the base of the Q1. Discharges into the base of the Q1 here. Right. So thus Q1 is again on and Q2 is off. So continuously this process will take place. Q1 is on, Q2 will be off position, and next one will be Q2 is on, and Q1 will be off. And again, next position, Q2 will be off and Q1 will be on here. Right. So like this will be continuously takes place, and you are going to be get what we call continuous oscillations you are going to be get here. So if you see uh, this switching time and frequency of vibration, this stable multi-vibrator here. So we'll draw the circuit diagram here. Sorry, this one. Frequency of oscillator. Okay. Yeah. So this is the current saturation position. This is ICEO. So this one is a Q1 is on, and this one is a Q1 is off. Yeah. So we have taken a square wave here, which is generated by the a stable multi-vibrator, right? So once we have taken this square wave, which is generated by the stable multi-vibrator, so which we have drawn here, right? So it is helpful for finding the value of what's called switching time and frequency. So now the time period T1 represents, so this is the time period T1 represents the duration for which the transistor Q2 is on, Q1 is off. Similarly, the time period T2 represents, okay, so here we write T1 represents for which the transistor Q2 is on. And similarly, the time period T2 represents the duration for which the transistor Q1 is on here. So automatically, whenever Q2 is on means at this position, Q1 will be off, you are going to be half. So here automatically, whenever Q1 is on means Q2 will be in the off position, you are going to be half. So both the time period T1 and T2 depends upon the charging and discharging of the capacitors C1 and C2. Okay, so this T1 it depends on charge of capacitor C1, and this T2 depend upon charge of capacitor C2. Okay, so this can be provided the time periods here. So generally, this will be T1 will be equals to you'll get 0.69 R1 C1 you are going to get. So this is nothing but Q1 is on time. So for Q1 is on time. And similarly for T2, similarly get 0.69 R2 C2 here. So this is for Q2 on time. So this is for Q2 transistor Q2 on time. So this is for Q1 is on time. So this is for Q1 is on time. So the total time period now becomes T is equals to T1 plus T2. So which will be equals to 0.69 R1 C1 plus R2 C2 you have. Okay. So for symmetrical a stable multivibrator, so R1 is equals to R2, comma, T1 is equals to T2, and similarly C1 is equals to C2. So that means T is equals to, total time T is equals to 0.69 RC plus becomes RC. So which implies T is equals to 1.38 RC becomes, because 2 into 0.69 you're getting it as a 1.39 RC we're going to get here. So from this, we can calculate the frequency of oscillations of this what we call a stable multivibrator. So here frequency, if we calculate, frequency is nothing but the reciprocal of the time period. So which will be equals to 1 by 1.38 RC. 1 by 1.38 RC. So if we do this one, generally you get around the 0.7 by RC you're going to get. So this is the case of the stable multivibrator. Okay, so this is the case of the stable multivibrator. So next we'll move to second one, that is a monostable multivibrator. Monostable multivibrator. Monostable multivibrator. So monostable multivibrator, it is also called as a one-shot or uni-vibrator we are going to record here. So in this case, if you see the circuit diagram of the monostable multivibrator, so we have again two transistors, Q1, Q2. So this is the first transistor. This is the first transistor for which resistance is connected here. And from here, you have resistance and capacitor, both are connected in parallel. So now it's fine. And we'll take here. From this here, it will be connected to next transistor here. This is Q2. Q fine. So all these are connected to the ground. All these are connected to the ground. Okay. So now for this one also collector resistance is connected. So now here we have one more resistance R2. This is the capacitor. This is the collector capacitor. And from here we get the output here. And these resistors are connected to plus VCC. So this is a RC1. This one is a RC2. This is one resistance and capacitance. And this is another resistor R2C2 here. Okay. So this is R1, C1, you can say that here is RC. So this is what the circuit, this is PC will call here. This is what the circuit diagram of monostable multivibrator. So it provides a single pulse of desired duration in response to an external trigger here. So the external trigger causes the circuit to go to the quasi-stable state. After a certain interval of time, the circuit returns to its original state. The circuit arrangement is shown here as in this figure. So it consisting of again two identical transistors. One is a Q1. This one is a Q1. This is a Q2 transistor. This is a Q2 transistor. So these two identical transistors with equal collector loads you are going to be have here. So the output of the transistor Q1 is coupled to the base of the Q2 to the resistance R here. Here to the resistance R, and the output of the transistor Q2 is coupled to Q1 to the capacitor C2 here, to this capacitor C2 here. The capacitor C2 is known as a speed up capacitor here. Its function is to speed up the circuit in making the abrupt transitions between on and off states. The output of a monostable multivibrator is available at the collector terminals of these transistors Q1 and Q2. Q1 or Q2. However, the outputs are complete complements of each other. That is, when one of the output is at VCC level, the other output will be at KCC saturation level you are going to be having. So generally, if you see the operation of this monostable multivibrator, so when the power is switched on, that is VCC is on, the transistor Q1 conducts and transistor Q2 is in cutoff position. Okay, when VCC is on, Q1 it conducts, Q1 conducts, Q2 will be in the cutoff position it is going to be have. Okay, so Q1 will be conducts and Q2 is in cutoff due to vertical reverse bias of the battery VBB. Due to the reverse bias of the battery VBB here. So this is what we have VBB. This one. Okay, VBB here, and it is in the reverse bias mode. Okay. This situation will maintain by the circuit unless the external pulse is applied from the terminal P2 here. So which will make transistor Q2 is in the forward bias and on. The transistor Q2 will remain on state unless until again you will give the pulse. So this is the pulse 1, pulse 2, whichever we have. Okay. So which if you unless until if you apply the pulse, it is going to be off position. So this sequence of continuously on and off positions through the by the resistors, by the transistors Q1 and Q2, they are going to be continuously in on or off position. You are going to be have alternately. So which will be generated as usual. We have seen like a square wave is going to be generates. So this is what the operation of the monostable multivibrator. So in this case, the thing is we have to give the pulse here. Pulse here we have to give. So whenever we will give the external trigger pulse, so it is going to be moved from on and off position. Again, from off to on position, it is going to be moved. So as in the case of the what we call a stable multivibrator, it doesn't require any external trigger pulse. So continuously, it is going to be changes its state from on to off to on here, depending upon the transistors Q1 and Q2, whether they are in on or off positions. Okay. So whereas in the case of the monostable multivibrator, we have to give external trigger pulse so that it has to be come down to the off position, then after to the on position. So now the width or duration of the time here. So duration of the time of the pulses obtained by the collector or the output of the transistors Q1 and Q2 of the monostable multivibrator is given by T is equals to 0.69 R2C here. This is R2C. So this is given by T is equals to 0.69 R2C. So this is what are the time period. So from this, we can calculate the frequency of oscillation, that is 1 by T. So this is a monostable multivibrator which we have. So these are the two different types of multivibrators which we have seen. So in the next class, what we'll see is we are going to see uh, bistable multivibrator we are going to be seeing, so that we can complete the multivibrators. Okay. So as we have discussed, so these are the multivibrators. Multivibrator is nothing but it is an oscillator. Otherwise, we can say that it is a two-stage amplifier. So one of the output is connected to the input of the next amplifier, which we have seen here. So input for the first amplifier, then it will connect it to the output of this transistor. Feedback is applied in the case of the multivibrator. So this is the block diagram of the multivibrator we have. Okay. So we have seen different types of multivibrators like the astable, monostable, bistable multivibrators. We have three types of multivibrator. So this is a stable multivibrator. So in which we are using two similar transistors Q1 and Q2. So in this case, uh, 180 degrees of phase shift is produced by one, another 180 degrees is produced phase shift here. So total 360 degrees of phase shift or 0 degrees of phase shift is going to be there. So whenever VCC is switched on, VCC is switched on. So through this RC1, this capacitor is going to be charges, and then after it is going into Q1 is an on position and Q2 is off position. So once it is charged, Q2 is then again a VCC. From this VCC, this current is going to flow to this RC2. C2 will be charges, and this Q2 will be on position. Q1 will be off position. So like this continuously, you are going to produce this square wave generator. You are going to produce here. So continuously the on position, on off position, you are going to get. In this case, no trigger pulse is required. Whereas in the case of and the frequency of oscillation is given by, we have to calculate the time period. T is equals to V of 0.69 RC, that is a 2 RC. So frequency is nothing but 1 by T. So we got 1 by 1.38 RC we have got. So this is what a stable multivibrator. Then monostable multivibrator, this is what we have. So in this, the difference is we have to give external pulse, we have to give so that it will be pushed from on position to off position. So again, external pulse whenever we are going to be give, so we are going to get on to off position continuously. So these are the two multivibrators which we have. So in the next class, we'll see about next one, that is a bistable multivibrator.